A bustling metropolis once flourished in the heart of a sun-scorched desert. This is the story of how ancient desert cities engineered water systems that rival, and in some ways surpass, our modern capabilities. You will discover forgotten technologies that mastered nature without destroying it. We will uncover how an empire built hidden tunnels to command rivers beneath the sand, and why a lost city's downfall holds a critical warning for us today. By the end, you will see our technological progress in a completely new light. What forgotten wisdom from the past could solve our greatest challenges today? Endless waves of sand stretch to the horizon, a sun-baked expanse where survival itself seems impossible. Yet here, in the heart of this arid emptiness, rose magnificent cities of stone. The silence of the desert is broken only by the whisper of a timeless question. How could such vibrant life exist in a place so defined by its lack of water? This is the desert's great paradox. For ancient engineers in places like Petra or Palmyra, water was not a convenience, it was an obsession. The sheer pressure of supporting thousands of people in a land that received mere inches of rain each year forced innovation on a scale we can scarcely comprehend today. Modern hydrologists studying these sites often express a sense of awe at the improbability. One expert noted that founding a major city here was akin to deciding to build a metropolis on the moon with the technology of the time. It was an act of breathtaking ambition, so what drove them to such extremes? Why choose this struggle against nature's will? The answer lies not in defiance, but in a profound understanding. These cultures saw opportunity where others saw only emptiness. They were motivated by trade routes, by security, by a deep connection to their land, and by a simple, unshakable truth. Where water flows, civilization follows. Their challenge became the catalyst for some of the most ingenious engineering the world has ever known, solutions born from necessity that would go on to shape their destinies. To label something as beyond modern capabilities feels like a contradiction. We live in an age of smart grids and massive desalination plants, yet this perspective hinges on a single, narrow definition of capability, one measured in horsepower and processing speed. The true genius of these ancient systems reveals itself when we shift our focus from power to harmony. A leading voice in sustainable engineering recently observed that our modern approach often treats water as a problem to be conquered with energy, while ancient cultures treated it as a partner to be guided with patience. This is the critical distinction. Modern engineering excels at high-energy, high-intensity solutions that demand constant input and control. Ancient engineering mastered passive, low-energy design that worked with natural forces, not against them. Think of it as the difference between a powerful pump that forces water uphill using electricity and a cleverly sloped channel that uses gravity alone to guide water for miles. One requires constant fuel and maintenance, the other simply understands the lay of the land. The metrics of success change entirely. Longevity becomes the ultimate test. A system that operates for centuries without fossil fuels or complex machinery demonstrates a profound kind of efficiency. Resilience is another key measure. How does a system handle a sudden drought or an unexpected flood? Ancient designs often incorporated buffers and redundancies that allowed them to absorb shocks and recover, functioning more like a living ecosystem than a rigid machine. This symbiotic relationship with the environment is what we are only now beginning to fully appreciate and strive to replicate. Our technological prowess is undeniable, but it often creates fragile solutions. Theirs created enduring legacies. Understanding this fundamental shift in perspective is the key that unlocks the real mystery of the desert. It allows us to see the landscape not as a barren wasteland, but as a complex hydraulic engine waiting to be understood. The sun-baked plains between the Tigris and Euphrates gave rise to humanity's first great experiment in urban living. This is Mesopotamia, the cradle of civilization, and its entire story is written in water. The great rivers provided life, but they were wildly unpredictable, flooding with violent force one season and shrinking to a trickle the next. The genius of the Mesopotamians was not in fighting these rivers, but in learning to converse with them. They became the first great hydraulic engineers, building the world's initial large-scale irrigation networks. Canals, some wide enough for small boats, branched off from the main rivers like veins from an artery. These man-made channels carried precious water deep into the surrounding farmlands, transforming a landscape of risk into one of remarkable abundance. They constructed sturdy levees, earthen walls to contain the destructive spring floods, and vast reservoirs to store water for the dry months. This was a complete system of water control, one that turned unpredictable nature into a reliable agricultural partner. But the true marvel was not just the physical infrastructure, it was the social organization it required. Archaeological evidence from ancient city-states like and Uruk reveals intricate systems of communal management. Surveyors used precise levels and simple geometry to ensure canals maintained a perfect, gentle slope for miles, a feat requiring incredible skill. Water distribution was governed by strict laws and overseen by administrators, ensuring every farmer received a fair share. This early innovation solved the basic problem of survival in an arid land, but it also laid a critical foundation. It proved that human societies could reshape their environment on a grand scale. So how did these early efforts pave the way for even more ambitious desert projects? The answer lies in the lessons learned. Mesopotamia provided the blueprint, the fundamental principles of moving and managing water across great distances. The next generation of engineers would take these principles into lands with even less water, where the challenge was not controlling a river, but finding water where none seemed to exist at all. A line of circular scars marches across the barren plains, a mysterious pattern visible only from above. These are the access shafts of a qanat, the hidden arteries of ancient Persia. Deep beneath the desert floor, a gently sloping tunnel carved by hand over generations carried a constant, cool stream of water for dozens of miles, all without a single pump. This was not a structure built to dominate the landscape, but to collaborate with it completely. Its brilliance began at the mother well, a deep shaft drilled into the base of a mountain range where water seeped slowly from the rock, feeding a hidden aquifer. From this starting point, skilled surveyors used nothing more than sighting rods and an intuitive grasp of gravity to chart a path downhill. Teams of workers, known as mucanes, would then dig the main channel, one painstaking meter at a time, ensuring its slope was just steep enough to keep the water moving, but gentle enough to prevent erosion. The vertical shafts we see on the surface served a dual purpose. They provided air for the diggers and a means to remove the excavated earth, but their most critical function came after construction. These shafts became permanent access points for maintenance, allowing communities to descend and clear silt from the tunnel, ensuring the life-giving flow never stopped. This was not a project for a single lifetime. The knowledge required to build and sustain a qanat was a communal treasure passed from father to son. It demanded a profound understanding of geology, hydrology, and geometry, all held within a single, dedicated guild of engineers. Historians note that these systems were so effective that some have operated continuously for nearly 3,000 years, sustaining entire cities in regions where surface water vanished for years at a time. The qanat's efficiency is almost unbelievable to modern engineers. Because the water flows entirely underground, it is completely protected from the relentless desert sun, with virtually no loss to evaporation. It requires no external power, only the constant, silent pull of gravity. This is the epitome of sustainable design, a system that gives far more than it takes. The concept was so successful that it spread along trade routes from the oases of North Africa to the arid stretches of Central Asia. But the Qanat represents only one form of desert genius. What happens when a civilization faces a different kind of water challenge, not a hidden aquifer, but the rare and violent deluge of a desert storm? A narrow canyon of rose-red stone rises on either side, its walls so close they seem to whisper secrets of the past. This is the majestic entrance to the lost city of Petra. But the true wonder here is not just the stunning geology, it is the subtle, carved channels running along these towering cliffs, the ghost of an ancient plumbing system that defied the desert. The Nabataeans did not just build a city in this canyon, they engineered a complete hydraulic machine. Their entire civilization was built upon a single, brilliant principle: to capture every single drop of water that fell from the sky. In a land of brutal flash floods and long droughts, they saw the violent desert storms not as a threat, but as their primary water source. At the very mouth of the Sick, they constructed a monumental dam, a masterwork of diversion. When a sudden flood roared down the canyon, this structure did not try to stop the immense power of the water. Instead, it gently guided the deluge away from the main entrance and into a specially carved tunnel, a bypass that safely channeled the destructive force around their city. This was the first step in a breathtakingly sophisticated system. Inside the Sick itself, those carved channels and terracotta pipes collected not only the floodwaters but also the precious seepage from the canyon walls, water that would have otherwise been lost. This network funneled everything into a vast array of underground cisterns, some large enough to hold the water supply for thousands of people for months. Over 200 of these reservoirs have been discovered, carved directly into the bedrock beneath the city. This was their strategic reserve, a buffer against years of poor rainfall. The result was a desert capital that could boast of public fountains, lush gardens, and even Roman-style baths. How did this watery abundance translate into power? Control the water, and you control the lifeblood of the desert trade routes. Petra became the ultimate oasis, a mandatory stop for every caravan carrying incense, silk, and spices. The city's wealth was not mined from the rock, it flowed from the ingenious management of a resource everyone else lacked. The Nabataeans thought in watersheds and seasonal cycles, their entire urban plan an extension of the natural landscape. They listened to the desert, and in return, the desert allowed their city to bloom. But this mastery of water raises a profound question. If their systems were so advanced, so perfectly adapted to their environment, what could possibly have caused such a powerful city to eventually fade from history? High on a sun-bleached mesa, a silent city rests within the cliffs themselves. The ancestral pueblones of Mesa Verde did not merely inhabit this harsh landscape, they listened to its rhythms with a profound intimacy. Their survival depended on a delicate dance with the scarce rains, a challenge they met with engineering so subtle it appears to grow directly from the stone. They understood that in the high desert, water was not just a physical resource, it was a sacred gift. This spiritual connection transformed their entire world into a carefully designed water catchment system. Their cliff dwellings were not randomly chosen, they were positioned with precise hydrological intent. The vast, flat tops of the mesas acted as natural collection plates for rainwater. The people engineered these surfaces, smoothing areas and carving shallow channels to guide the precious runoff toward the cliff edges. There, meticulously placed stone spouts and carved grooves in the rock face would direct the water down into waiting reservoirs or into seeps within the alcoves where they built their homes. This was a direct harvest, capturing water before it could be lost to the thirsty soil below. But their genius extended far beyond the cliffs. In the dry washes known as arroyos, where sudden storms could create violent, brief torrents, they built small, resilient check dams. These were not structures meant to create large lakes. their purpose was far more sophisticated. By slowing the rushing water, the dams allowed it to soak deep into the ground, recharging the aquifers that fed the springs they relied upon. They were managing the entire water cycle on a community scale, thinking in terms of slow absorption rather than rapid diversion. An anthropologist who has studied these sites for decades notes that for the ancestral Pueblones, water management was a ceremonial practice. The physical act of building a dam or cleaning a channel was an act of reciprocity with the land, a prayer made manifest in stone. Their engineering and their cosmology were one and the same, a seamless whole where every terrace, every reservoir, and every dwelling was part of a living, spiritual landscape. This deep integration of belief and practicality created a system of profound resilience, allowing their culture to flourish for centuries in a land of extreme scarcity. It reveals a universal truth that the most enduring solutions often arise not from a fight against nature, but from a reverent partnership with it. The legend whispered for centuries spoke of a city of unparalleled wealth, a place of towering pillars and immense sin, punished by the heavens and swallowed whole by the shifting sands. This was Ubar, the Atlantis of the sands, a cautionary tale seemingly lost to myth. Yet beneath the fable of divine retribution lies a far more compelling truth, a story written not in fire and brimstone, but in water and geology. The real Ubar did not vanish in a single cataclysmic event. Its fate was sealed by a fundamental misunderstanding of the very resource that gave it life. Nestled at a critical crossroads of the frankincense trade, Ubar's power was built upon a geological fluke. The city was constructed directly above a massive limestone cavern, a natural cistern that held a vast treasure of fossil water. This was not a renewable supply from recent rains, but ancient water, trapped deep underground for millennia. The people of Ubar became masters of this hidden aquifer, engineering intricate well systems that tapped directly into the cavern, drawing up the cool, ancient water to sustain thousands of people and the endless caravans that were the source of their wealth. They built vast catchment areas on the surface, designed to funnel every rare desert downpour into the cavern below, actively recharging their precious reservoir. Satellite imagery and ground-penetrating radar have since revealed the ghost of this system, a sprawling network of channels and well shafts converging on a single, massive sinkhole. For generations, this symbiotic relationship with a deep, non-renewable source worked perfectly, but fossil water is a finite inheritance, not a sustainable income. The very success of Ubar contained the seeds of its decline. As the city grew richer and its population expanded, the demand on the water reserve intensified. The careful balance between extraction and natural recharge was inevitably broken. Research suggests that the final chapter may not have been a sudden collapse, but a slow, grinding exhaustion. The water table dropped, the wells began to run dry, and the lifeblood of the caravan trade slowly ebbed away. The city that was built on a secret ocean of water was ultimately defeated by its gradual disappearance. The sands did not swallow Ubar out of punishment. They simply crept back in once the water that held them at bay was gone. This loss highlights a profound vulnerability in even the most advanced ancient systems. Their brilliance was hyper-local, a deep, intimate knowledge of a specific place. When that knowledge was lost, or when the delicate balance it maintained was disrupted, the entire civilization built upon it could falter. This raises a haunting parallel for our own time. How many of our modern marvels are built upon resources we assume are endless? Descending into a stepwell feels like entering an inverted temple, a palace built for water itself. Carved deep into the earth, these breathtaking structures of India are where architecture and hydrology merge into a single, glorious discipline. They were not merely holes in the ground to draw water. They were monumental feats of engineering designed to solve a very specific problem, the dramatic seasonal fluctuation of the water table. During the scorching dry season, the water level could retreat dozens of feet below the surface. A simple well would become useless, its life-giving water impossibly far out of reach. But the stepwells, with their breathtaking cascades of steps and terraces, descended to meet the water, ensuring access no matter how low it fell. Their construction was a masterclass in anticipating hydraulic pressure. The immense weight of the earth pushing in on the excavated pit required incredibly robust design. Builders employed a series of heavy stone columns and arched galleries to buttress the walls, creating a structure stable enough to withstand the forces of the surrounding soil and the occasional monsoon deluge. This was not just digging, it was architectural counterpressure, a carefully calculated dance with the very ground it was built into. But the true magic of the stepwells lies in their dual soul. They were intensely practical, yes, but they were also vital social and spiritual centers. As people walked down the long, cool staircases to collect water, the journey became a daily ritual. The further you descended, the more the temperature dropped, offering a blessed respite from the heat above. The ornate pavilions and carved niches built into the walls provided spaces for community gatherings, for markets, for quiet contemplation. This was a place where the essential chore of survival was elevated into an art form. The walls are covered in intricate sculptures depicting deities and mythological scenes, a constant reminder that water was sacred. Here, the line between a water tank and a place of worship completely dissolved. The stepwell stands as a powerful testament to a culture that refused to see infrastructure as purely functional. For them, a solution to a physical necessity could and should also nourish the community spirit and honor the divine. This holistic approach created an enduring legacy where every step downward was a step toward life, culture, and connection. The silent, carved channels of Petra were far more than simple gutters. They were the heart of a hydrological network so advanced it redefined the very purpose of an aqueduct. While the Romans built their iconic stone bridges to span valleys in a show of imperial power, the Nabataeans engineered for invisibility and preservation. Their aqueducts were not meant to be seen but to survive. Instead of soaring across the landscape, these channels were often carved directly into the solid rock of cliff faces, becoming one with the mountain. When they had to cross open ground, the Nabataeans built them as low, covered conduits, shielding the precious water from the relentless desert sun and wind. This simple design choice had a profound effect. It all but eliminated the catastrophic water loss through evaporation that would have plagued an open Roman-style channel in such a climate. It also protected the supply from blowing sand and contamination, ensuring the water reaching the city's cisterns was as pure as the day it fell. The true genius, however, lies in the gradient. Modern surveys of these channels reveal an almost unbelievable precision. The slope is consistently gentle, often as little as a few centimeters drop over a kilometer of distance. This was not a compromise, it was the core of the design. Such a minimal gradient allowed the water to flow at a slow, steady pace, just fast enough to prevent stagnation and silt buildup, but slow enough to minimize erosion and the powerful suction effect that could collapse a tunnel. This meticulous control meant the system could run for miles without the need for the massive, energy-intensive arches and pressurized siphons that characterized Roman engineering. The Nabataean philosophy was one of supreme efficiency. They worked with the desert's constraints, using minimal energy input to achieve maximum conservation. Their goal was not to move the largest volume of water in the most dramatic way possible, but to ensure that every single drop collected from a brief desert storm was delivered safely to its destination. In a context of extreme scarcity, this focus on sustainability and loss prevention created a system arguably more resilient and better adapted to its environment than any Roman aqueduct. It was a quiet, brilliant answer to a question of survival, proving that the most sophisticated solution is not always the most monumental, but the one that understands its home completely. High on the mist-shrouded slopes of the Canary Islands, the wind carries a hidden treasure. For the ancient Guanches people, the dense, persistent fog rolling in from the ocean was not an obstacle, it was a river in the sky. Their innovation was breathtakingly simple, yet it tapped directly into the atmosphere's own cycles. They observed that certain local trees, like the hardy laurel, were constantly dripping with water, even on days without rain. The trees were acting as natural fog collectors, their leaves and branches condensing the tiny water droplets from the fog into a steady trickle. The Guanches replicated this natural process by constructing large, vertical screens from woven vegetation or piled stones. They positioned these screens strategically in mountain passes where the fog was thickest, and the wind pushed it through their collectors. As the fog-laden air passed through the dense mesh, countless microscopic droplets would collide and stick to the surfaces, gradually coalescing into larger drops that gravity would pull downward. Channels at the base of the screens then captured this freshly made freshwater, guiding it into cisterns or directly to their fields. This was atmospheric water generation, centuries before the term existed. It provided a remarkably reliable source of clean water in a volcanic landscape with very little consistent rainfall. What makes this approach so profound is its radical redefinition of a water source. The Guanches were not digging for groundwater or damming rivers. They were harvesting water directly from the air itself, turning a climatic condition into a life-saving resource. Today, modern scientists and engineers are looking back to these ancient methods with renewed respect. In arid regions from Peru to Nepal, you can now find vast grids of modern fog-catching nets, made from advanced synthetic fabrics that operate on the exact same principle the Guanches perfected. These projects are providing vital water for reforestation and rural communities, proving that this ancient wisdom holds a key to addressing modern water scarcity. This example forces us to expand our own thinking. It reveals a layer of hydraulic genius that looked beyond the obvious sources, understanding that water could be drawn not just from the earth but from the very breeze. Hidden beneath the dense Cambodian jungle, the sprawling stone temples of Angkor were merely the visible peak of a far greater achievement. The true wonder of the Khmer Empire was its hydraulic heart, a water network so vast it functioned as an artificial river system for a metropolis of nearly 1 million people. While their temples reached for the heavens, their canals and reservoirs mastered the earth, turning the extreme cycle of monsoon and drought into a predictable rhythm of life. At the center of this system were the immense barrays, rectangular reservoirs so enormous they were essentially inland seas. The largest, the West Barray, stretches over 5 miles long and 1 mile wide, an expanse of water held back by earthen embankments that still inspire awe. These were not just for storage, they were the empire's strategic water bank. During the relentless monsoon rains, a complex web of canals would divert floodwaters into these giant basins, preventing the low-lying urban center from being swamped. Then, during the long, rainless months, a carefully controlled release of this stored water would flow back through the canals to irrigate vast rice paddies, ensuring 3 harvests a year in a land that would naturally support only one. This was a complete man-made hydrological cycle. Recent LIDAR surveys have peeled back the jungle canopy to reveal the stunning truth. The entire landscape was a precisely engineered grid. Beyond the monumental canals, a fractal pattern of smaller channels, field boundaries, and ponds managed water on a neighborhood scale, distributing it evenly across the urban expanse. This was a system of unparalleled complexity, a metabolism for a city built on water. Yet, this very success contained a hidden fragility. The system required constant, meticulous maintenance, a communal effort to dredge canals and repair embankments. Research suggests that a combination of prolonged droughts and intense monsoon seasons, possibly linked to a shifting climate, began to overwhelm the delicate balance. The very channels designed to bring life may have, in periods of extreme flood, contributed to severe erosion, washing away the agricultural foundation they were meant to sustain. How could something so advanced, so perfectly calibrated, eventually falter? The story of Angkor serves as a profound reminder that no engineering, no matter how brilliant, exists in a vacuum. It is part of a delicate conversation with a climate that is never truly static, a partnership that requires constant, attentive care. While the giant geoglyphs of the Nazca Desert capture the world's imagination, their true purpose may be written not in the sprawling lines, but in the spirals carved directly into the earth. Scattered across the same arid plains, these strange, funnel-shaped holes known as Puquios have long puzzled archaeologists. They are the visible signature of a hidden masterpiece, an underground water network that turned one of the driest places on the planet into a land of sustainable farms. The Nazca did not just draw on the desert surface, they engineered a way to make the desert itself provide water. The secret lies in the spiral design. These were not simple wells. The Puquios were connected to horizontal tunnels that ran for miles, tapping into deep underground aquifers. The spiral shape itself was the engine. As wind swept across the open desert, it would funnel down into the Puquios. The corkscrew design accelerated the air, creating a difference in air pressure between the top of the shaft and the tunnel below. This pressure drop acted like a gentle, continuous siphon, pulling water from the aquifer and pushing it through the underground canals to the surface, where it could irrigate fields. It was a wind-powered aqueduct, running on nothing but the natural forces of the desert. How could a culture with no known written language design such a sophisticated system? They possessed a profound empirical genius, a deep knowledge gained through generations of careful observation and experimentation. They understood the physics of wind and water pressure not from textbooks, but from a lifelong conversation with their environment. This was engineering as an extension of intuition, a perfect marriage of form and function that allowed life to flourish against impossible odds. The lines on the surface may point to the heavens, but the spirals reveal how the Nazca listened to the very breath of the earth. A caravan of 10,000 camels moves like a slow river across the dunes, their bells a quiet music in the vast silence. This was the lifeblood of the Silk Road, a network of trade that connected continents. But its true foundation was not the silk or the spices. It was the carefully placed dots of green that made the journey possible at all. The desert was not a barrier but a carefully managed corridor, and its gates were the oases, each one a triumph of hydrological engineering. Without these way stations, the entire global economy of the ancient world would have simply ground to a halt in the sand. The systems that fed these oases, known in Central Asia as qanats, were the unsung heroes of international commerce. Like the qanats of Persia, these were underground channels that tapped into mountain aquifers, delivering a steady, cool flow of water to the surface at precisely the points where the caravans needed to rest. The water would emerge into a central pool surrounded by date palms and gardens, a sudden explosion of life in the emptiness. This was not a passive gift of nature. It was a created, maintained reality. The management of a qanat was a science passed down through generations, with communities dedicating themselves to the constant, careful maintenance of the tunnels to prevent collapse or siltation. But the importance of these water points extended far beyond local survival. Control of a major oasis meant control over a choke point in global trade. The authority to grant or deny water to a passing caravan was a form of immense economic and political power. This made the oases centers of not just commerce, but of delicate international diplomacy. Treaties were signed guaranteeing safe access to water. Armies were sometimes deployed not to conquer cities, but to secure these vital hydraulic hubs. A dispute over water rights could disrupt the flow of goods from China to the Mediterranean. The engineered oasis, therefore, was more than just a water source. It was a diplomatic tool, a strategic asset, and the fundamental infrastructure that allowed ideas, religions, and technologies to flow across the world. The desert flourished with life because human ingenuity had woven a hidden web of water, turning the most inhospitable places into the very centers of connection. The Moche people gazed upon a landscape that seemed to defy the very idea of civilization. Their domain was a narrow strip of coastal desert in Peru, squeezed between the vast Pacific Ocean and the soaring Andes Mountains, a land where rain might not fall for years at a time. Yet here they built monumental adobe pyramids and thriving cities. Their survival depended on a single, audacious act of engineering, capturing water at its source high in the mountains and guiding it across dozens of miles of barren plains to their fields. They did not wait for the sky to provide. They reached into the Andes and commanded the rivers to flow where they needed them. The backbone of their empire was a network of irrigation canals of staggering scale and complexity. Some of these channels were massive, wide enough to serve as small waterways in their own right, branching and splitting into a fractal pattern that delivered life to every corner of their territory. This was not a simple ditch dug in the earth. It was a permanent, engineered landscape. To prevent their canals from simply dissolving back into the desert, the Moche developed a form of hydraulic cement, a concrete that could set and harden even underwater. They mixed local materials, creating a durable lining that could withstand the constant flow without eroding. This single innovation gave their water system a longevity that simple earthworks could never achieve. But perhaps their most sophisticated understanding was of the river itself. They knew the water coming down from the Andes was not just water. It carried a heavy load of sediment, sand, and silt that would gradually fill their canals, choking them from within. So they designed their system with a profound knowledge of fluid dynamics. They built settling basins, large, calm pools where the fast-moving water would slow down, allowing the suspended sediment to sink to the bottom before the clearer water continued onto the agricultural channels. This meant their canals required far less frequent dredging and maintenance. Their entire approach was built on a long-term, strategic vision. They were not just solving the problem of this year's drought, they were building a hydrological machine that would function for generations. By harnessing distant, seasonal water from the Andes, they transformed a coastal desert into a verdant breadbasket, capable of supporting a complex society with artisans, priests, and warriors. Their success, however, hinged on a delicate and distant balance, a reliance on climatic patterns far beyond their direct control. A simple ceramic bowl, carefully pierced at its base, held the power to prevent conflict between neighbors. In the sun-baked farmlands along the Nile, the fair distribution of water was not just a matter of convenience. It was the bedrock of social order. Canals could bring the river's gift to the fields, but without a way to measure a farmer's allotted share, chaos would reign. The solution was a technology of beautiful simplicity, the water clock or clepsydra. It measured time not by the shadow of the sun, but by the steady, relentless drip of water from one vessel into another. A farmer's right to irrigation might be granted for the time it took to fill a large pot, a unit of measurement that everyone could see and trust. This was time made liquid, a transparent and impartial judge. The genius of this system lay in its adaptability. In Babylon, clepsydry evolved into far more complex devices, with multiple chambers and scales to account for the changing flow rates at different water levels, ensuring accuracy throughout the day and night. This was not merely a timer, it was an instrument of civic governance. By linking water rights to measured intervals, these ancient societies codified fairness. They transformed a potentially contentious resource into a scheduled, predictable utility. The local water master, armed with a clepsydra, could mediate between families, ensuring that a farmer upstream did not take the share of a farmer downstream. This integration of timekeeping with resource management represents a conceptual leap as significant as any dam or canal. It highlights that the most brilliant hardware is useless without the software of equitable administration. The physical network of channels was the body of the water system, but the clepsydra was its beating heart, a metronome for civilization that kept the entire community in rhythm with the resource they all depended upon. The spiral of a Nazca Puquio and the perfect rectangle of an Indian stepwell are more than just functional shapes. They are a silent language, a form of prayer written in stone and water. For countless ancient engineers, the act of designing a water system was a spiritual act, a collaboration with the divine to bring order to a chaotic world. They operated on a profound belief that a structure built with geometric harmony would, in turn, create harmony in the water it carried. This was the principle of sacred geometry, where the circle, the square, and the spiral were not just mathematical ideals but representations of cosmic balance. In the stepwells of India, this philosophy is breathtakingly clear. The entire structure is a mandala, a symbolic map of the universe descending into the earth. The perfect symmetry of its levels, the precise repetition of its arches, and the mathematical progression of its steps were all intended to honor the sacred nature of water itself. The builders were not merely constructing a reservoir, they were creating a temple where every line and angle was a form of worship, a plea for the continued blessing of a steady flow. This spiritual drive for perfection had a powerful, practical consequence. A perfectly symmetrical structure is inherently more stable. A channel laid out with precise alignment and a consistent gradient does not clog or erode easily. The quest to please the gods, it turns out, resulted in designs of remarkable hydraulic efficiency and longevity. This challenges our modern separation of science and faith. We often see them as opposing forces, one dealing with cold, hard facts and the other with intangible belief. But in the ancient world, they were inseparable partners in problem solving. The spiritual imperative to build something perfect pushed the boundaries of engineering knowledge. It demanded a deeper understanding of mathematics, a more careful observation of natural forces, and a commitment to craftsmanship that transcended mere utility. An expert in the history of science might note that the alignment of an Egyptian temple with the Nile's flood cycle was both an act of religious devotion and a sophisticated form of hydrological forecasting. The geometry was the bridge, a language that spoke equally to the gods and to the flow of water. This fusion of purpose created systems that were not only brilliant but also resilient, cared for by communities who saw them as living expressions of their deepest beliefs. The legacy of sacred geometry asks us a compelling question. In our pursuit of purely functional solutions, have we lost a dimension of meaning that once gave our greatest creations both their elegance and their enduring strength? The echoes of past greatness are often followed by a profound silence. For every desert city that mastered its water, another eventually faltered, its story ending not with a bang, but with a whisper of sand filling an empty canal. The collapse of these civilizations offers a different kind of wisdom, a cautionary tale written in dried-up riverbeds and abandoned reservoirs. The evidence is stark. In Mesopotamia, the very irrigation canals that created an agricultural paradise carried the seeds of its own destruction. Each flood season, the Tigris and Euphrates deposited tiny, mineral-rich particles of silt into the carefully dug channels. Over generations, this silt accumulated, slowly raising the level of the canals and the surrounding fields. This created a hidden hydrological trap. As the farmland rose higher, the water from the rivers could no longer flow onto it by gravity. The system required constant, back-breaking dredging by a vast, organized labor force. When political instability or social unrest disrupted this maintenance, the entire agricultural foundation began to fail. The land, now starved of water, became poisoned. With no fresh water to flush it away, salt drawn up from the subsoil accumulated on the surface, creating a white crust that choked the life from the wheat and barley. What was once the Fertile Crescent gradually turned into a salinized landscape, its productivity fading with each passing season. This was a slow-moving disaster, a failure not of initial engineering but of long-term systemic maintenance. Meanwhile, on the Arabian Peninsula, cities that thrived on fossil groundwater faced a different reckoning. Their immense success at drawing up ancient, non-renewable water led to a quiet crisis of depletion. The water table, that hidden ocean beneath the sand, began a relentless retreat, sinking further from the reach of their wells. The energy required to lift the water grew exponentially until it was no longer feasible. These were not sudden catastrophes, but a gradual unraveling. Paleoclimatologists studying ancient tree rings and lakebed sediments have found that many of these collapses coincided with periods of extended, severe drought. A water system perfectly calibrated for normal variability could be broken by a mega-drought lasting decades. A society might survive one dry year or even 5, but when the rains fail to return for a generation, even the most brilliant engineering can reach its limits. In some cases, the very social structures that enabled these massive projects became a liability. A rigid, top-down administration, so effective at mobilizing labor for construction, could become too inflexible to adapt to a rapidly changing climate. The rules for water distribution, carved in stone for centuries, might not be rewritten quickly enough when the rivers ran low. The central authority, its power derived from controlling water, might resist the decentralized, local solutions that could have offered resilience. The lesson from the dust is not that these civilizations were foolish, but that their success made them vulnerable. They built marvels designed for a specific world, and when that world changed, the marvels became monuments to a different time. So what does this mean for our own sprawling metropolises, many of which are now tapping into aquifers that will not recharge in our lifetime, or relying on river systems pushed to their absolute limit? The past suggests that the greatest threat may not be a lack of technology, but a failure of foresight, the inability to see the slow, silent shifts that ultimately define our future. For centuries, the full extent of this hydraulic genius lay dormant, its blueprints erased by sand and the slow creep of forgetting. The knowledge that once sustained empires was fragmented into scattered ruins and local legends, a ghost in the landscape. Today, a technological renaissance is pulling these secrets back into the light. A new generation of archaeologists, armed with tools their predecessors could scarcely dream of, is mapping this lost world. High above the Earth, satellites peer through the veil of time. Multispectral imaging detects subtle differences in soil moisture and plant growth, revealing the ghostly outlines of buried canals and long-vanished farms. These spectral signatures paint a picture of ancient watersheds on a continental scale, showing how entire regions were engineered for water flow. On the ground, LIDAR systems fire millions of laser pulses from aircraft, stripping away dense jungle canopy or layers of sand to create a perfect, three-dimensional map of the ground beneath. This is how researchers discovered the true, staggering complexity of Angkor's suburban grid, a fractal pattern of water management invisible to the naked eye. In the deserts of the Middle East, the same technology has exposed the vast, sprawling networks of Qanat shafts, showing how these systems connected entire regions into a single hydrological web. But the investigation goes even deeper into the very chemistry of the Earth itself. By extracting long cores of sediment from ancient lakebeds and reservoirs, scientists can read the climate history of a civilization like the pages of a book. The layers of silt and pollen tell a story of wet periods and devastating droughts. Isotopic analysis of the elements trapped within that sediment can even trace the specific water sources a city used, revealing when a society shifted from local springs to distant mountain rivers, or when their wells began to tap into ancient fossil aquifers. This is not merely an academic exercise. The data from these sediment cores provides a precise timeline, correlating periods of social upheaval with specific environmental pressures. We can now see how a multi-decade drought strained the social contracts of a water-sharing society, or how a series of catastrophic floods overwhelmed even the most brilliant diversion channels. This revival of ancient knowledge is building a direct bridge to our present challenges. Contemporary engineers and urban planners are now studying these passive, gravity-fed systems as blueprints for a more resilient future. The principles of the Qanat are being adapted to provide sustainable cooling and irrigation in arid regions. The fog-catching techniques of the guanches are being scaled up with modern materials to harvest drinking water in coastal deserts. We are finally learning to listen to the past not as a distant echo, but as a conversation partner offering solutions we desperately need to relearn. Gravity was their only engine. These ancient engineers mastered a form of magic that required no fuel beyond the Earth's own gentle pull, creating systems that ran for centuries on a power source that never faltered. This is the sustainability principle in its purest form, a stark contrast to our modern reliance on intense energy inputs. Consider the immense electricity required by a contemporary desalination plant, forcing salt from seawater to make it drinkable. It is a brilliant feat, but one that demands constant, costly power. Now place that beside the silent, sun-powered elegance of a Qanat. Its water flows cool and protected underground, shielded from evaporation, moved by a force that costs nothing and never bills the community. Modern ecological engineers often speak of these designs with a sense of reverence. One noted that the true mark of sophistication is not complexity, but elegance, a system where every element serves multiple purposes with minimal waste. The ancient approach was fundamentally holistic. They did not fight the landscape, they listened to it. A canal was not just a trench, it was a carefully calculated part of the watershed. A reservoir was positioned to capture not only rain, but also the seasonal flows from specific slopes, integrating the entire natural system into a single, functioning whole. This is the lesson we are painfully relearning today. True advancement may not lie in building more powerful pumps, but in designing smarter channels. It asks us to shift our definition of progress from one of domination to one of partnership, to see the wind, the sun, and the slope of the land not as obstacles, but as collaborators in the timeless challenge of survival. The silent, unyielding stone of an aqueduct holds a secret modern labs are racing to decode. While we marvel at the grand scale of ancient water systems, their true resilience often lies in the microscopic world, in the very stuff they were made from. Ancient engineers did not have synthetic polymers or industrial steel, yet they developed building materials of such sophistication that some are actively healing themselves today. Take Roman concrete, the bedrock of their legendary aqueducts. Modern analysis has revealed it was a carefully calibrated mixture of lime, volcanic ash, and chunks of rock. The Romans would combine this with seawater, a process that would seem like a recipe for disaster to any contemporary builder. Yet this very combination is the source of its magic. Over centuries, seawater slowly seeps into the concrete, reacting with the volcanic ash and lime to form new, crystalline structures that fill in any tiny cracks that form. It is a living material, constantly repairing itself from within, a capability our own concretes utterly lack. This was not a lucky accident. It was the result of generations of empirical testing, a deep understanding of local material properties gained through tireless trial and observation. This material wisdom extended across the ancient world. In the Indus Valley, builders lined their crucial canals and large public baths with a remarkably effective waterproof layer. They created a dense, impermeable lime plaster that could withstand constant submersion, preventing precious water from seeping back into the thirsty earth. The process of creating this plaster required precise control over the heating of limestone and the careful slaking of the resulting quicklime, a dangerous chemical process mastered thousands of years ago. Their choices in stone were equally deliberate. In Petra, the Nabataeans selected specific types of sandstone for their water channels, rock with a natural density and mineral composition that resisted erosion from both flowing water and abrasive desert sands. They understood that not all stone was equal, and their selection ensured their carved channels would last for centuries. This profound, practical chemistry challenges our assumptions about technological progress. These builders achieved a near-perfect synergy between their materials and their environment, creating infrastructures that were not imposed upon the landscape, but were a durable, lasting part of it. Their legacy is a quiet question. In our pursuit of stronger and faster, have we forgotten the value of creating things that can simply endure? A technological marvel is useless without the people who care for it. The most brilliant aqueduct or qanat would have crumbled into dust within a generation if not for a social contract, a shared understanding that bound the community to its lifeline. This was the true, hidden strength of ancient water systems, a governance of shared destiny. In Valencia, Spain, a unique court has met every Thursday for over 1,000 years. The Tribunal of the Waters gathers in front of the cathedral doors, its 8 judges, all farmers elected by their peers, settling disputes over irrigation channels in a matter of minutes, with no written records and no possibility of appeal. Their authority comes not from a king or a code of law, but from the collective trust of the community. This living institution resolves arguments with a speed and finality that modern courts might envy, all based on oral tradition and deep, localized knowledge of exactly how much water a specific field requires. Across the world in Iran, the vast underground networks of qanats were sustained by a similar social fabric. A council of elders, often including the muqannis who built and maintained the tunnels, would oversee the water distribution. The allocation was not based on wealth or power, but on a precise, time-based share. A farmer might own the right to 1 hour of the total flow every 12 days, a portion measured by the shadow of a stick or the slow filling of a ceramic bowl. This meticulous scheduling required constant cooperation and a profound sense of collective responsibility, for if one section of the tunnel collapsed, the entire community would suffer. The Moche of Peru took this a step further, weaving water rights directly into their spiritual and political hierarchy. Their leaders were not just rulers, they were the ultimate water masters, responsible for the celestial harmony that brought the rains from the Andes. The allocation of water to different valleys and clans reinforced social order, turning the physical flow of water into a symbol of power and fairness. The system only functioned because everyone, from the highest priest to the lowest farmer, understood their role in its upkeep. This deep integration of technology and social structure created a powerful resilience. It meant that maintenance was not a burdensome tax, but a shared ritual of survival. When a community sees its own fate reflected in the clear flow of a canal, it protects that flow with a passion no central authority can ever command. The stone and clay were only half of the engineering. The other, more vital half was the human heart. The resilience of these ancient systems was not a matter of luck, but a product of continuous, thoughtful adaptation. Civilizations understood that their environment was a living, breathing partner that could change its rhythm without warning. In the sun-scorched landscapes of the American Southwest, the Hohokam people left behind a powerful testament to this philosophy. Their sprawling canal networks, etched across what is now Arizona, were not a static monument. They were a dynamic, responsive conversation with the sky. Scientists studying the patterns in ancient tree rings and the layers of sediment in long dry lakes can now read this conversation. The data reveals a clear story of climatic pulses, periods of generous rainfall followed by severe, multi-year droughts. The Hohokam response was a masterclass in flexibility. During the good years when the rivers ran high, they expanded their canal systems, reaching out to bring water to new fields and support a growing population. But when the tree rings tightened, telling a tale of prolonged dry spells, the archaeological record shows a strategic retreat. They did not stubbornly cling to their entire network. Instead, they contracted, focusing their maintenance and water flow on a smaller, more manageable core of canals, ensuring the survival of the community even as its footprint temporarily shrank. This was not a sign of failure but of profound intelligence. Their engineering was designed for this very ebb and flow, and their social structures were fluid enough to manage the redistribution of a scarcer resource. This built-in capacity to adapt, to scale up and down with the climate's rhythm, is what allowed them to thrive for nearly 1,000 years in one of North America's most volatile environments. Their legacy offers a critical blueprint for our own time. We face a global climate that is shifting in ways we are still learning to predict. The Hohokam model suggests that our greatest strength may not lie in building bigger, more rigid infrastructures, but in designing systems with humility and flexibility at their very core. How do we engineer for a future that refuses to stand still? A gentle murmur of water echoes through sun-drenched courtyards, a sound as deliberate as any blueprint. This was the final layer of ancient hydraulic genius, where pure function blossomed into breathtaking art. In the heart of Moorish Spain, the intricate qanat systems did not simply end at a wellhead. They emerged as the centerpiece of the Alhambra's palaces, where mathematics and moisture met in perfect harmony. The channels fed ornate fountains and serene reflecting pools, their surfaces mirroring the intricate arabesques carved into the surrounding stone. The sound of trickling water amplified the cool stillness of the courtyards, a sensory masterpiece designed to evoke paradise itself. This was engineering in service of beauty, a deliberate creation of an environment that soothed the spirit while it quenched physical thirst. The water's journey from the hidden mountain aquifer to the elegant palace fountain was a single, unbroken line of purpose. Across the world, the same principle guided the creation of Japanese gardens. What appears to be a perfectly natural stream meandering through mossy stones is, in fact, a meticulously engineered component of a larger irrigation network. The gentle flow is calibrated, the placement of each rock designed to control water speed and aeration for the surrounding rice paddies or vegetable plots. The serenity of the scene is not an accident. It is the result of a profound understanding that a system which pleases the eye and calms the mind is also one that people will care for with devotion. This fusion transformed the entire city into a living work of art. Canals became graceful promenades, reservoirs became placid lakes for contemplation, and public fountains became gathering places adorned with sculpture. The act of drawing water was elevated from a daily chore to a moment of communal interaction and aesthetic pleasure. This integration reveals a universal truth about these cultures. They refused to separate the needs of the body from the longings of the soul. For them, a perfectly engineered solution was not truly complete unless it also contributed to the beauty of the world, creating spaces that inspired wonder and reminded every citizen of the profound, life-giving grace of water itself. Our modern world moves water with breathtaking force, pushing it through concrete arteries with immense pumps and energy-intensive treatment plants. This approach achieves something ancient engineers never could, delivering safe, reliable water on a colossal scale to millions of homes and safeguarding public health through advanced sanitation. We can command rivers to change course and transform ocean water into a drinking supply, feats that would have seemed like pure magic in the ancient world. Yet this power comes with a hidden fragility, a constant demand for fuel, complex chemicals, and intricate maintenance. When the energy fails, the water often stops. In contrast, the ancient systems we have explored were masters of patience. They worked on the principle of guidance rather than force, using gravity's silent, eternal pull to move water for miles without a single watt of electricity. Their genius lay in minimizing loss, designing channels to protect against evaporation, and building with self-repairing materials that grew stronger with time. They measured success not in the volume of water moved per hour, but in the number of centuries their system continued to function. This creates a fascinating dichotomy. Modern engineering provides incredible scale and safety, while ancient principles offer unparalleled sustainability and resilience. So which path is the right one? The answer is not a choice between them, but a vital synthesis. Imagine a future water grid that combines the best of both worlds. What if our powerful desalination plants were paired with restored watersheds that mimic ancient sponge cities, absorbing floodwaters and recharging aquifers naturally? Could our smart municipal networks draw inspiration from the communal water courts, using digital platforms to foster transparent and equitable local management? The true breakthrough will come not from abandoning our technology, but from layering it with a deeper wisdom. It is about building systems that are not only smart, but also wise, that can harness the sun and the wind and the slope of the land as collaborative partners. This integrated vision, blending the muscle of the modern with the mindfulness of the ancient, may be our most promising path through the water challenges that lie ahead. The quiet hum of a modern water pump is a sound of undeniable power, yet it cannot answer the deeper questions posed by these silent, ancient channels. Our journey ends not with a final answer, but with a renewed sense of perspective. We have walked through inverted temples built for water and traced the paths of wind-powered aqueducts, discovering that true capability is measured not in horsepower but in harmony. The legacy of these desert engineers is a masterclass in listening to the land, a testament to what becomes possible when we work with nature's gentle forces rather than overwhelming them. The core principles they embodied are more relevant now than ever: sustainability achieved through elegant design, community as the essential caretaker of any system, and the resilience that comes from adaptive, flexible thinking. These are not dusty artifacts in a museum of ideas. They are living blueprints. They challenge us to reconsider our own relationship with the resources that sustain our modern world, to see our challenges not as puzzles requiring more energy, but as opportunities for wiser design. So we leave you with this final reflection. Which of these ancient marvels reshaped your understanding of ingenuity? Was it the hidden, breathing tunnels of the Qanat or the cliff-carved harmony of Petra? Share the system that amazed you most and join us as we continue to uncover the profound wisdom hidden in the mysteries of our past.